So what we're going to look at here is we've got a short assignment on prime factorizations, greatest common denominators, GCDs, and least common multiples. And these actually end up being really, really important for us doing any work when it comes to integer representations, any kind of modular arithmetic, and also any kind of number theory. So we'll start out with an idea of what it means to be prime. Okay? So a number x is prime if, prime, if it has only two. Now, by the way, two and only two factors. Only two factors, one and itself. So basically, a number x is prime if it can only be divided by 1 in itself. So 7, is only divisible by 1, or 7 can only be divided by 7, right? Everything else, not divisible. Now, when we talk about divisibility, we want to make sure that we know that this is only integer division, okay? We're not talking about like dividing by fractions. What we know is, right, 1 will divide 7, 7 will divide 7, and that's it. Okay, so 7 is prime. On the other hand, we have this idea of what it means to be composite. And what it means to be composite is that a number x is composite if and only if it has more than two factors. Okay? So it's already got 1 in itself. That's always going to happen, right? So like say, for example, we take 12. We know that 1 divides 12. We know 12 divides 12. Okay? But we also know that 3 will divide 12. And 4 will divide 12. Okay? And 6 will divide 12. And 2 divides 12 as well. So 12 actually has 1, 2, 3, 4, 5, 6 factors. 6 factors for 12. So we're going to use these definitions of prime and composite in order to actually do something called prime factorization. And so I think the best thing to do is to talk about what we're trying to do with prime factorization. When you prime factoring, so prime factorization is a representation of all of the prime factors of a number x. All right? And in these factorizations, we use exponents to represent multiples of a particular factor. All right? So what I'm going to do is I'm going to use a factor tree in order to show you actually what this looks like. Okay? So let's say, for example, I want to prime factorize 256. Okay, so I got 256. And I'm going to look at 256, and what I want to do is I want to actually break it up into its primes. So 256, I can look and I can see that it's even. And since it's even, that means I can divide it by 2. All right? So your factor tree is going to look to just divide through by integers until you can divide by nothing else other than 1. Until all of the things that you divided by each what we call branch of the tree end up being all primes. So this gives me 2, and it'll be 2 times 128. And that's 256. Now, we notice that 2 is prime, so we go to 128 and we say, okay, can I divide 128? Well, 128 divides by 2. Okay, so that's 2, and that's going to be 2 times 64. All right? Now, this particular branch of the tree ends, and I'm going to go to 64. 64 is divisible by 2, so that's 2 times 32. 32 is divisible by 2, so that's 2 times 16. 16 is divided by 2, so that's 2 times 8. 8 is divisible by 2, that's 2 times 4. And so you'll notice that all I'm doing is, in this case, I'm dividing by particular factors. So now 2 times 4, and then we have 2 times 2. And now the factor tree is over. It's finished. Because what we have is at the end of each one of what we call our branches, okay, each one of these branches, we have prime factors, right? You can see this factor ends because both of those are prime, both are 2's. So there are all of our prime factors. So this number, we created a factor tree, okay, to demonstrate all the different factors of 256. So now what I'm going to do for my prime factorization, 256 is going to equal, I'm going to multiply all my prime factors. So it'll be 2 times 2 times 2, that's 1, 2, 3, 4, 5, 6, 7, 8. I've got 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 5, 6, 7, 8. So I've got the 8 2's, and what I'm going to do is I'm going to write them as 2 to the 8th. So 256 equals 2 to the 8th power. And that is the prime factorization. And so that's how you prime factorize. Let's take a look at another example. So let's take, for example, that I use now B, and it's 2,304. And I want to create a prime factorization. We'll do that using a factor tree. So I got 2,304. I'll divide by 2. That's 1,152. And now I can divide by 2 again, because it's an even number, and that's now 576. And 576 is even, so I can divide by 2 again. That's 288. 288 is divisible by 2, so I got 2 again. Okay. Now 144. 144 is divisible by 2. That's now 72. That's 2. 2 times 36. Then we'll divide by 2. 2 times 18. 18 is still even. And what you'll notice is that as I'm factorizing, I'm always going to start out with like the smallest prime. In this case, like 2. Okay? And I'm just going to divide through. So now I've got 2 times 9. And now 9 is not divisible by 2. But it's okay because it's clearly divisible by 3. So we got 3 times 3. And now all of the ends of my branches, they're now all prime. What I'll do now is I've got 2,304. I'm going to write this as an exponent. So that's 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 2's, so that's 2 to the 8th, times, and I got 2 3's, so it's going to be 2 to the 8th times 3 squared. So you got 2 to the 8th times 3 squared. So now go in and try out C and D. Okay? That is, create a prime factorization for 1404 and also a prime factorization for 31,752. Okay, so that's C and D. Go ahead and pause the video so that you can go through and do that. I'll give you the answer, but you're going to have to go in and show all of your work as to how you got the prime factorization. So now that you finished that, we've got 1404 is going to equal 2 squared times 3 cubed times 13. So go ahead and take a look at that, see if you got the same thing. And then 31,752 is going to equal 2 cubed times 3 to the 4th times 7 squared. So those are your prime factorizations. One key hint here is that I went through and like I said, I divided by 2 until I couldn't any longer. Then I went up to the next prime. The next prime here is 3, right? Okay. And so I kept dividing by 3 until I couldn't divide by 3 any longer. And then you know, what I ended up with actually was 13, so it actually wasn't that hard to figure out what the next prime was, because it was clearly 13. We want to kind of do that. We're going to keep increasing the primes and testing them out until we get a better manner or a better method for selecting the primes that might be part of our prime factorization. Okay? Now, the next two ideas that we're going to do are going to be the greatest common denominator, okay, or the greatest common factor, the GCF or the GCD, and the least common multiple, or the LCM, or the least, yeah, there it is, least common multiple. So let's start out with the GCD, or greatest common divisor, actually, is also one of the phrases. And what we're going to see is the GCD is the GCD of x and y, right? So we got our definition here, is going to equal the largest number, or the largest integer, excuse me, the largest integer that divides x and y. So it's got to divide, so it's got to be in common, all right? And it's a divisor, so it divides both x and y, okay? And it'll be the biggest integer that it will do both. So let's say, for example, I want to figure out GCD, okay, of 256 and 2,304, okay? So I look at those two. Now we actually have a method, all right, where we use the prime factorization. So we're going to using the prime factorization in order to do this. What we're going to do is we're going to use all the common factors. So I'm going to go in here and I'm going to actually look at my two factors. I've got 2 to the 8th times 3 squared, that's 2,304, and 2 to the 8th is 256. Okay? So I got the 256 equals 2 to the 8th, and 2,304 is equal to 2 to the 8th times 3 squared. Now, what I want to do is I want to find all the prime factors that they have in common. And if you look here, 256 has 8 2's, and 2,304 also has 8 2's. Okay? So they have all of those factors in common. And when we think about that, that means actually that I can divide through 2,304 by 2 8 times. Just like I can do the same thing with 256. Okay? So, consequently, if I look at this, this means, right, 2 to the 8th is what both have in common. All right? And 2 to the 8th actually equals 256. So 256 is the GCD. It's the thing they both have in common. So that's 256. You can actually look, and 256 does divide 2,304. In fact, 256 times 9 will equal 2,304. Okay? Clearly, there is no bigger divisor for 256 than 256, right? Because if you pick a number that's bigger, you're going to end up with a fraction, and that clearly is not a divisor for 256. So this gives us an example, right, where we go out, we find all the factors that these numbers have in common, okay, and that ends up becoming our GCD. Okay? Now, let's try this out with both the two other values. We're going to find the GCD. So we want to find the GCD of 256 and 1404. So go ahead and pause for a second. See if you can find that. Great. Now let's take a look at this. What we're going to do now is we're going to set up 256 once again is equal to 2 to the 8th. And 1,404 is 2 squared times 3 cubed times 13. If we look here, 256 doesn't have any 3's or 13's in it, so we're not going to include that as part of our GCD. And even though 256 has 8 2's as its factor, 2 to the 8th, we only have 2 squared as part of 1404. So the GCD of 256 and 1404 is just what they're going to have in common. It's going to end up being 2 squared, which equals 4. Okay? So now, let's try the last one. You do the last one on your own. It's B, and it's going to be find the GCD of 31752 and 1404. So go ahead, pause, and find that GCD. What you'll need to do is you'll need to show the work that you used in order to actually do the prime factorization, and then I'll give you the answer at the end. The GCD for both of these, if you look at it, is going to end up equaling 2 squared times 3 cubed, and that's 4 times 27, and that's 108. So that's the GCD of those two numbers. Okay? I guess this would actually be B and C. If we look at your worksheet. Now finally what we're going to look at is this thing called the least common multiple. So the least common multiple, called the LCM, LCM of x and y is the smallest number. We'll call it z. The smallest number z, or smallest integer z, pardon me, integer z, such that z equals a times x and z equals b times y for some a and b belonging to the integers. Okay? So that's going to be our least common multiple, and it should be the positive integers, I would say. So what we're looking for is we're looking for a number, okay, that we can divide both of our values into, okay, that have all of the factors, right? So LCM of x and y will have all of the factors of x and y. So for example, if we take the GCD of 256 and 2,304, or excuse me, the LCM, then what we're going to see is that 256, right, is 2 to the 8th, and 2,304 is 2 to the 8th times 3 squared. So what we'll want to notice, what we do is we say, okay, well, I'll take all of the factors of 256, so that LCM is going to equal 2 to the 8th. We've got all of those. Now, in 2,304, I already have the 2 to the 8th. I just need the remaining 3 squared. So we're going to remove all of the doubles or the repeats, and that'll give us our LCM. Okay, so we've got 256 times 3 squared, so the LCM actually turns out to be 2,304. And it makes sense, right? Because 2,304 equals 1 times 2,304, and 256 is going to equal, and 2,304 is also equal to 256 times 9. So 2,304 is a multiple of both 256 and 2,304. All right. Now let's take a look at one more. We'll do this next one together too. We were going to find the LCM of 1,404, 2,304. Okay. So we already have 2,304 is equal to 2 to the 8th times 3 squared. And 1,404 is equal to 2 squared times 3 cubed times 13. So we'll start out here. We're going to need our 2 to the 8th. So I got 2 to the 8th. So my LCM is going to have 2 to the 8th, all of those. And then I don't need the 2 squared because I've already got 2 to the 8th. Then I'm going to multiply by 3 squared. That's this thing right here. I got 3 squared. And so what you'll notice, I have 3 squared already, but I'll need an extra one to get to 3 cubed. So times 3. and then times 13 because that's my remaining factor. So what this gives me is it gives me that my LCM is going to end up being 89,856. So all you do here is you take all the factors, okay, that the you take all the factors of one of your values x and y, and then what you'll do is any factors that are not in x, right, but that are in y, you're going to multiply them into your LCM. Okay? And so you'll notice I've got 2 to the 8th, right, that's in there. 3 squared, that's there too. I have the 3 cubed, okay, there's the 3 cubed that I need, and I have the 13 that I need as well. And this 2 squared comes along for the ride because it's part of 2 to the 8th. Okay? And that's how I find the LCM. So, here's what I want you to try out. Go ahead and find the LCM for 256, 31,752. So you've already done the prime factorization for that. Now go in and find the LCM. So, my LCM now is 1,016,064. Okay, so make sure that you got that as well for your LCM. And that completes this lesson on prime factorization. Pretty short, pretty quick, right? Okay, we've got these 2 big ideas, least common multiple, greatest common divisor. Okay, so make sure you go in, you check up on what you've got there, submit your completed worksheet, and you are done. Have a great time. Have a great weekend.